Okay, now we're going to look at multiple linear regression, and this is an extension of the last video. We'll be using the same data set with some added data in here as well. And the difference between a multiple linear regression and a simple linear regression is the number of predictor variables. While we were constrained to one predictor variable for a simple linear regression, for a multiple linear regression, we can use as many predictor variables as we would like. And so I don't think it's too much more complicated than what we went through in the last video, although there are some important additional considerations. I will say the one additional, or a additional, n additional assumption that we need to consider is multicollinearity or collinearity. And that's the idea that some of our predictor variables might be too much like another predictor variable to the point where they're measuring the same thing or close to the same thing. And we are not happy to have, we would not like to have that in our analysis if they are. And that's a simple option that we're going to select while we run our tests that will tell us if we are running into that problem or not. So I guess we're going to hop right into it, and I'm going to spend the majority of this video showing you a few different ways that you can run this analysis. I'm not an expert on all of these different ways, but I hope to give you a general impression of what each different way, what the differences are between each way to go about running a multiple linear regression. So we're going to go up to Analyze. We're going to go to Regression, Linear, and we're going to put income back in there, and we're going to pop in age just like we had before, and now we got two additional variables: the number of kids a participant has and the highest education level that they've achieved. And I think I labeled highest education 1 through 6 from some high school to doctorate. And we're going to select a few more options here. We're going to check off confidence interval, and we're going to run the gamut here and select all of these. I'm going to click continue plots. We're going to do our predictive on our x-axis and residual on our y-axis, histogram, normality plot. That's all good. Continue. I think that might be all we need for now. And what we're going to be doing this is running this a few different ways. And the first way we're going to do this is running them all simultaneously. It's just going to be one model. All three predictor variables ran at the same time. And the only thing you need to do that is keep this as enter and click OK. All right. So the first thing I'm going to do is show you this collinearity statistic. And the first subcategory we'll look at is tolerance. And we want this to be greater than 0.1. And what that tolerance collinearity statistic represents is how much variability is not explained by the other independent variables. So if this was only 0.05, we could say, oh, that is explained by this other variable. Let's say instead of highest education level, or in addition to highest education level, we also had total numbers of study hours in one's life. And we find that that is highly correlated with highest education level to the point it might be measuring the same thing. We might not include that in our analysis, and we would know that by looking at this. Don't know, I'll be honest, I don't know what this variance inflation factor represents, but I hear that it has to be less than 10, and it looks like across the board we're less than 10, so that's wonderful. We're going to hop back up here to our ANOVA to see that our model predicts income level greater than chance would, so that's wonderful. Our R squared has increased from 0.3 something when we were just looking at age, all the way up to 0.722, and if we adjust it, 0.69. So 69% of income's variance can be predicted by looking at these three other variables, which is good. I mean, that's a pretty high predictive level. So wonderful. And if we go down to our coefficients table, let's take a look here. So this B value represents the same thing that it did the last time. For every unit increase, we can see this much increase in our income level. So every additional kid is going to yield us $5,000 less in income, and every level of education greater is going to yield us $7,300 more dollars. And of course, we need to look at our confidence intervals to see the actual range of what that value represents in the real world. And we also want to look at our beta levels to see kind of a more comparable number, because this is looking at how many standard deviation movement and income level based on a single standard deviation movement in our predictor variable. So let's head over to significance level. And what's interesting here is that age is no longer a significant predictor of income level. When we added these two other variables in here, that must have accounted for all of the significance that was within age, and it's no longer significant. So that's an interesting finding. If we go over to these correlations, these will tell us the degree, the amount of unique contribution that each one of these variables have to the variability or variation in our outcome variable income. And we can see out of the gate here, it's not surprising that our least significant or our unsignificant variable of age contributes the least amount at 0.129, and that our highest contributor is highest education level at 0.365, and our second highest is number of kids at negative 0.358. Okay, now what we're going to do is just look at a few other ways that we can run this analysis and kind of give you a brief overview of what each one does. So I'm going to close out of that. We're going to go back to our regression dialog box here, and the first thing we're going to do is to add each one of these into different blocks, and we're going to do that manually. So in block 2, we're going to add in number of kids, and in block 3, we're going to add in highest education level. And this is going to give us 3 different models, and the third model is going to look, I'm assuming, exactly like the one we just looked at, because that will be a model that's looking at all 3 of them simultaneously. So we're just going to go ahead and click OK. And if we go down to model summary, we can see that our first model is looking at age, our second model is looking at age and number of kids, and our third model is looking at age, number of kids, and highest education level. And I'll have you pay special attention to the R-square change here and see what this actually represents. That's telling us that you can see the R-square change is the same thing as the number itself for the first predictor, and then every level beneath it, the R-square change is going to be added on to the previous R-square to give us our new R-square total. So that's telling us how much more of our outcome variable can be predicted when we add each additional variable. And sometimes it's subtracted. It's not always added. We could add a variable when we add it in. It's going to tell us less about income. But it just so happens that for all three of our variables right now, we can see that the more variables we look at with the variables that we have, the greater power we have to predict income level. So great. And if we go down here, this is kind of neat because it's going to give us a little more information, and it'll show us the different predictions for each different model. So we have our predictions when we're just looking at age exclusively, when we look at age and number of kids, and when we look at age, number of kids, and highest education all together. What I think is very interesting to note is if we look at the unique contribution, we can see how it goes from significant to insignificant. So for the age variable specifically, where we had 0.60 or 60% over here, the part correlation. And once we added a number of kids, that's telling us a lot of the variability in income level is the variation of income level that age predicts shares a whole bunch of that with number of kids. And if we add an additional variable, even more of that prediction, more of that variation is shared with highest education level to a point where it becomes insignificant if we're looking at all three variables together. All right. So quickly, we're just going to run through three other ways to do this here. And we're going to get more significant, roughly speaking, as we go along. So now we're going to not make these decisions on our own. Oops. And we're going to throw them all into the same block together. And we're going to change our method from enter to forward. Now what this is going to do is it's going to develop a model based firstly on which variable contributes the most variance or predicts the most variance of our outcome variable. And it's going to piece by piece add a variable to each model that will predict some more. So let's just click OK and see what we get. So if we go down to our model summary, it's no surprise here that highest education level, everything we looked at before, told us that highest education level was the greatest predictor of income level. And so it's no surprise that the algorithm chose to look at that first. And all on its own, it accounts for 52% of the variation in income level. And when we add number of kids, we increase to 68%. And what's interesting or noteworthy is the algorithm decided not in any model to include age. And again, that's something that's not surprising, given that we saw that its contribution, when we kind of shoehorned it in there ourselves last time, was insignificant. Its contribution was insignificant. So why include it? And we're going to see some similar, although not necessarily identical, results down here. All right. We're going to go back to our dialog box, and instead of forward, we're going to choose backward. And what backward is going to do is basically the opposite of forward. It's going to take all of them together as the first step, and then it's going to subtract the predictors that are contributing the least step by step. So we're going to go ahead and click OK. We'll see out of the gate, the first predictor is looking at 3 of them, and the second one, it removed age, no surprise, and it's only looking at highest education level and number of kids. What's interesting is that it didn't go one step further to only look at highest education level. It said no, number of kids is too important of a contributor, and that's as far as we're going to go. And feel free to look over the coefficient table. It's going to look similar to the ones we've looked at before. And on to our last and most significant method of multiple regression is going to be the stepwise function. And this is going to be some combination of the forward and the backward functions that we just did. And it's my understanding what happens is it will start with forwarding or forward up the predictor that is the highest correlator, that has the highest predictive value of the outcome variable. It'll use that for model 1, and it will continue to add additional predictors. But sometimes if you have a bunch of predictive values, if you add one variable, then suddenly one that you were looking at became less predictive, and it might decide to delete that one later. So it's some combination of the forward and backward. That's about what I know. And I'm imagining this is not going to look all that much different than our forwarding correlation that we had, or our forwarding regression that we had before. So if we go down, we can see highest education level was our first model, and highest education level and number of kids was our second model, and what is not included is a third model looking at all 3. That was not determined a significant enough predictor to use. And so there you have it.